This recording today is going to be a little bit awkward for reasons I'll talk about here in just a few minutes. Um, but I wanted to give you a little bit of a basic basis for or explanation of what's been going on. I mentioned, excuse me, in a previous video that my summer plan was to create shorter videos with content specifications specific for the ASRT examination. So that was what I had intended to spend my summer doing this year. So summer started well, and I started by recording a few general information application, how to be successful videos, and posting those onto the YouTube page. And I think there was value in those, but what I found was that it takes a long time to create PowerPoints that drives these. So I got to the end of summer and hadn't accomplished what it was that I'd set out to do through the summer. And then towards the end of the summer, I got sick, and I'm still battling that. This is third week into the fall semester. I'm still battling that. I'm not in the classroom yet. I'm recording videos, putting them online. So hopefully, I'm hoping to be back in the classroom next week, and things will return a little bit to normal, even though we've got our reaccreditation through the JRCERT this year. So that's going to occupy some of my time as well. So what I create when I do create content is I take the publisher's software, and that's why I give credit to the publishers of Bushong in this case. And when I do positioning, it will be three different textbooks, and that will be the Merrill's, Atlas, the Bontrager's, and also Martinson's radiographic critique. And we'll get into that probably in the next video. I'm going to try to record two different videos today. So what I don't do is take the PowerPoint from the publisher and just recite what they have on there. So about 10%, and primarily the images that come with publisher software is what I use. The rest of it is my own content and things that I add, either because of personal experience, professional experience, or things that I feel like students should know. So it takes a lot of time to create a PowerPoint. I would say uninterrupted somewhere around 8 hours. If I'm dealing with other things, like I'm having to deal with accreditation right now, then it's closer to 12, 13 hours just to create a PowerPoint that'll give me about a 40-minute lecture. So a lot of time that goes into it, and most of the time it takes 2 days to put together a PowerPoint and edit it and make it make sense. So about 12 hours, 13 hours or so. And then when I record, it's an hour-long video, or 40 minutes to an hour-long video, followed by in our software that we use on campus is called Panopto. It takes a while for our videos to load up. I'm recording these from home, and I live in a land that internet forgot. So what I have to do is activate a hotspot on my phone in order to get internet to my computer, which means that it takes a long time, even a longer time, to upload these videos, to the tune of about 4 to 6 hours to upload a video. And once it gets uploaded, now it's got to be downloaded to my computer and saved onto my computer so that then I can upload it into YouTube. So to download onto the computer, probably 2 to 3 hours. And then upload into YouTube is typically about 1 to 2 hours. So by the end of all this, it's a minimum 15-hour commitment for a single video, and it's usually closer to 20, 22 hours. So easily 3 days, and in my compromised position right now, possibly more than that. So it's very, very time consuming. And I'm not complaining about that. I'm getting to a point here. I started this video page, or this YouTube page, to provide the videos for my students, and it's grown to over 1,100 subscribers. And I'm pleased. I'm tickled to death that it's done so, and I really appreciate the support. But what I want to do is I want to deliver content to help anybody who's working through a radiography program to be successful in their program. So it's a labor of love. I'm not getting paid. I don't have any kind of sponsors. If I eventually get to the point where YouTube, um, advertisement pays me something, then great. If not, then I still intend to put out content. The reason my eyes are going back and forth and all over the place is because I'm trying something new. My home computer is this computer. My work computer is this computer. So what I've done is on my home computer, I downloaded some software that enables me to record offline, so I don't have to have that hotspot activated. It'll record directly to my computer, and then hopefully I'll be able to take the recording and upload it directly into YouTube, so that it skips some of those steps, and it'll reduce the time by about a day that I can actually get a video online. So I don't intend to produce everything from home to put online, but if I do, then hopefully this will remove about a day's worth of work in trying to get it online. So instead of 3 days, it'll be 2 days. So that's why I'm going back and forth. Unfortunately, I only have one external microphone, so I'm hoping I bet on the right horse. I plugged it into my home computer. So if the home computer recording doesn't work and I have to lean back on the work computer recording, and if it sounds a little bit choppy, as it does, if I forget the microphone, then I apologize for that. Also, you're going to hear some background noise. I've got the windows open. It's a nice fall day for Northeast Texas in September. It's nice and cool outside, so you're going to hear the wildlife. You're going to hear my animals. I've got chickens, roosters, goats, dog. Neighbor's got a dog that comes around, but I'm also having some work done too. Some plumbing issues I'm having. So you're going to hear some background noise, and just kind of block that out. So I apologize for that. So what so far what I've noticed on my home computer is my color's a little bit off. To me, I look a little bit jaundiced. I don't have hepatitis. I'm not in liver failure or anything like that. So just understand that's the color that it chooses. I'll kind of try to adjust that over time and make it look a little bit better. So with that in mind, I'm going to review what it was that we talked about in the last recording. This is going to be the second and final part of Bushong Chapter 2. So I'm not going to go through everything in that we talked about before, the basic math, fractions, decimals, how to add, subtract, multiply, and divide, all those. I'm not going to do that. But we're going to come back up to the point of standard units of measurement. We're going to start our review there. So our standard units of measurement are used to ensure reproducibility of outcomes, and our scientific units of measurement our three standard units of measurement would be length, mass, and time. Then we have the special units, the radiation units that we talked about in Chapter 1. That would be the rad, rem, Rinkin, and Curie in the old terminology, or the Air-Kerma, Gray, Sievert, and Becquerel in the new. So when we talk about the length, our scientific measure would be our meter, but we also have other measures that we use, especially here in the States. We've got foot, yard, meter, or foot and yard, inches that we use here, but meter, kilometer, centimeter is pretty much used worldwide. We talk about where it was that we get those measurements. So we're just going to skip through that. We talked about mass being measured in kilograms, and we said what that represented. And we also reviewed again from Chapter 1 that it's not the same thing as weight. Weight is the gravitational effects on a mass. So we do use them kind of interchangeably, so we're not going to get a big twist about that. And then we use time, and that was just seconds. We talked about derived units and what those were. Derived units are any combination of units, be it the same unit more than once, or if we have a combination of units. So I use some of the examples, like a meter is just a base unit, whereas square cubic meter would be a derived unit, and kilometers would be a base unit. But if you're talking about speed, kilometers per second would be a derived unit. And then we talk about our how the measurements work, and we have to have two things. We have to have a unit, which is what we're measuring. So that would be your time, distance, or volume. So it would be your seconds, or your kilometers, or your kilograms. And then you have to have a magnitude. So one doesn't tell you anything, 1 kilogram does tell you something. So you have to have a unit and a magnitude in order to make sense of things. So then we got into mechanics, and we talked about velocity, velocity being speed, and it's how fast you're going, and that's distance traveled over a period of time. So V, velocity, equals distance over time. Average velocity was just like finding the average of anything else. You take the values that you have and you add them all together and you divide by the number of values that you have. So in this case, what we've got are two values. You've got an original velocity and you've got an ending velocity. So you add those two together and you divide by two to give you your average velocity. And acceleration would be the rate of change of velocity. So you speed up. So we talked about a couple of things in that. We talked about passing, a tractor on country road or whatever. But we also talked about the acceleration of gravity. Acceleration of gravity was a consistent rate, and that was 9.8 meters per second squared. And then we talked about why it all really matters, and that is because of the way we create X-rays. We're going to talk more about that today, so I'm going to skip through that until we get to it here in a little bit. We talked about Sir Isaac Newton and his three laws of motion. We have inertia, which is resistance to change. We have force, which is just as it sounds, is force. It's a pushing or pulling energy. And then we have action reaction. That is to say that for every action, there's an equal and opposite reaction. So again, inertia is resistance to change, and it is best known as body at rest stays at rest, body in motion stays in motion, unless acted on by external force. So force itself is just a mathematical equation, and the two components of force will be mass and acceleration. The higher either one of those have, the more force you have. So then I kind of gave you a thinking question, and that was about a guy skydiving from 140,000 feet. I'm going to get rid of that. I was going to open that for you, but anyways, skydiving from 140,000 feet, and he actually got up past what we recognize as terminal velocity. So the acceleration of gravity is 9.8 meters per second squared until you reach terminal velocity. Terminal velocity at sea level is about 250 miles an hour, roughly, give or take. But he actually broke the sound barrier and asked for answers in the comments on YouTube. Didn't receive any, so I'm just going to spill the beans here and say, going back to all of the Newtonian physics that we talked about before, you have acceleration of gravity, and you have action reaction. You have acceleration of gravity 9.8 meters per second squared, and that applied as he jumped out of the balloon. But the further he fell, what he ran into was resistance and air resistance. So at 140,000 feet, there's almost no atmosphere, so he had to wear the spacesuit, not only so he could breathe, but also so he wouldn't freeze to death. But as he fell through the atmosphere got more dense, and it pushed back up against him, and he slowed down. If he'd been traveling 800 miles an hour at sea level and he pulled a ripcord and his parachute came out, it would have killed him. But he slowed down to what we recognize as terminal velocity. And then if you, terminal velocity would be as if you were falling like a pencil. But if he flattens out, he slows down to about 120 miles an hour. He can pull the ripcord and he floats safely to home or to the ground. All right, so for every action, there's equal and opposite reaction. The force imparted on an object by another is shared between the two objects. So what we have a tendency to think of in action reaction is we watch movies and somebody gets shot and it blows them 10 feet away. And that's not how things happen. The action and reaction are two things. One, they're equal, and two, they're shared. Okay, so just reading the definition of action reaction, you would think that if you were pushing against something, that you're doing all the work, and you truly are. But the force, even though if like I'm pushing up against the table that both of these computers are sitting on, you're probably seeing it shake. The table is not providing an active push. It's pushing down with gravity and it's resisting the change in position. But where my hand is in contact with the table, we've got a shared imparted force between the two. So even though it's not actively pushing back against me, there is a push there, even though I'm doing all the work. So momentum is something you should be familiar with. Momentum, if you notice, is represented by P because we've already used M in mass. So momentum is mass times velocity. So again, the mass of an object increases, then your momentum increases. If the velocity increases, then your momentum also increases. So in mass, that's easy to see. And in mass, if you have a toy dump truck, rolling along at 1 mile an hour, it's easy to stop. It doesn't have a whole lot of momentum as opposed to a real dump truck. If it's rolling around at 1 mile an hour and you step in front of it, it's going to push you. So the larger the mass, the larger the momentum, but also the velocity as well. If you take that same toy dump truck and you roll it at 40 miles an hour, it's going to hurt you whenever it hits you. So remember your complex um, formulas. So what is velocity? Well, velocity is distance over time, distance traveled over time. So in each one of these, you're going to have to break down to learn the formula and the components of the formula. You're going to have to break down each one of these things. So mass is at its lowest possible value. Velocity has two components to it, and that is distance over time. So on the test, I'm just telling you, you're going to have to think deeper than just this right here. You're going to have to get into what each one of these things actually means. So work is a force applied to an object times the distance for which the force is applied. So again, it's kind of like momentum. Work in this case is going to be mass times our acceleration. So our ending velocity minus our original velocity over time. So again, we've got a time component there as well. Again, on the test, hope is going to be next Friday. Then you've got to break down each one of these. What does each one mean? Power is the rate of doing work. The greater the rate of work, the greater the power. And I'm just going to let you kind of read through all this. It's just work over time. So again, we got time in there. Energy is the ability to do work, and we've got a lot of different types of energy. So in the X-ray tube, we've got mechanical energy, we've got electric energy, we've got the potential energy, we've got the thermal energy that we've all already talked about, and we're going to talk about it again here in a minute. But we tend to skip over the mechanical energy. So we do see mechanical energy in the rotation of the anode. The reason that we rotate the anode, and I'll show you this in class, is that with the rotation of the anode, what we're doing is we're taking that big disk that the target is a part of, and we're rotating that around so that we can spread the heat out and increase the heat load in the X-ray tube. So remember, the main thing we create inside the X-ray tube is heat. And unfortunately, the heat's the main thing that's going to cause the X-ray tube to fail. So we've got to learn to deal with that heat. And one of the ways that we do that is to spin that anode as quickly as as is feasible, not as quickly as we can, but as quickly as is feasible, so that we change the area of bombardment of all those hot electrons or thermionic emissions or hot ions. We change the position with where they interact with that anode so that we can spread that heat out a little bit more. So it extends the life of the X-ray tube. If we don't do that, then in a lot of cases, what we're going to get is a warping or a melting of that target area, and that's not going to be good. It's going to shorten the life of the X-ray tube and reduce the output. So then we again have our potential energy, and remember, our potential energy is the unrealized kinetic energy. So it's stored energy at somewhere, right? In the X-ray tube, where we have the stored energy is on the filament before it travels from the cathode to the anode. So when you hit the prep button, two things happen, actually. One is you can hear the motor start to spin up, right? So that's your mechanical energy. So that's that mechanical sound, that motor sound that you hear is the rotation of the anode. And then you store those electrons on the filament before you send them across the X-ray tube. Once they travel across the X-ray tube, they become kinetic energy. But before they travel across the X-ray tube, they are just potential energy. You're not creating X-rays yet, not until you send them across the tube. So we call it potential energy because they're stored until we hit it with KVP and travel across the tube. So you have to have both the potential energy and then the KVP to send them across the X-ray tube. And this is all mechanical energy that's causing this to happen. So once we release those, we get the energy of motion, and that is our kinetic energy. And it's just another formula. I'm not going to require you to work that either. So what's the point to all this? And that is the work that we're trying to do is to create X-rays. We have to create a significant electric potential in our KVP, and that results in a very high kinetic energy that causes acceleration of electrons. They go from effectively 0 miles an hour to about, not really close to the speed of light, but maybe close to half of the speed of light. So their velocity is very, very quick in a short distance. The electrons have to carry enough power to overcome the binding energies, and I'll talk about that here in just a second, of the target atom, forcing an electron out of its orbit. So one electron has to hit another to knock it out of its orbit. At the same time, the gravitational pull on the nucleus of the projectile electron changes the electron's direction, changing its inertia, causing it to lose momentum. And so we've got two different ways that we create X-rays. One is, that I've already talked about, is breaking X-rays. That's your Bremsstrahlung X-ray, and that is all about losing momentum. The other involves the knocking out of the electron, and that's what we refer to as characteristic X-rays. So looking at the X-ray tube, what we do is, again, we have electric energy creating thermal energy, thermionic emissions. We create a lot of electrons, we stack them right here, and then eventually we send them across the X-ray tube with very high kinetic energy, with enough momentum to knock out an orbital electron, and carrying enough momentum too that whenever they strike the target atom, or the target, even if they don't hit an atom, they slow down very rapidly, lose momentum, and because of the law of conservation of energy, what we get is an X-ray photon created. So the two different ways that we create X-rays is with that slowing down. So if you notice, what we have is what we refer to as a projectile electron. So the projectile electron is an electron we send across the X-ray tube. This is an atom. We've got a nucleus, and it's not really reflecting the electrons in the shells, but that's what these rings are. Is not just rings like around Saturn, but they're rings with electrons inside of them. So those electrons didn't really matter for this particular picture, so it's not a big deal. But if the electron comes in and the gravitational pull of the nucleus of the atom is significant enough, if it gets close enough to the nucleus of the atom that it changes directions, then what's going to happen is it slows down significantly enough that it loses some energy. And in that loss of energy, what we get is a Bremsstrahlung X-ray photon. And here's the rub. If we send this across the tube with 100 kVp worth of energy, and it slows down to the point where it's only carrying 50 kVp worth of energy, then the energy level of that Brems X-ray photon is going to be 50. So it's going to be the difference between the incoming and outgoing energy of the projectile electron. But it didn't touch anything. So think of this as kind of like a comet coming through the solar system. The comet coming through the solar system, if it gets close enough to the sun or Jupiter, then it's probably going to change direction because of the gravitational pull of the sun or that planet and changes its direction. So this is kind of like a comet coming through the solar system, but the difference is that it's going to let go of an X-ray photon in the form of breaking, slowing Brems radiation. The other is characteristic. So if the recording off my personal computer is the one that actually posts, you've got the links. For whatever reason, my work computer wouldn't post the links, but it's from Radiopedia. And if you really need those, I'll provide it if the work computer videos is the one that posts. So what we have then is this incident electron. We're gonna call it a projectile electron. As a projectile electron enters the electron cloud, and if it hits a orbital electron and knocks it out of place, then what's going to happen is that you're going to have a vacancy in that shell, and another electron is going to drop into place. And what you're going to get is the squiggly line always represents X-ray creation. Straight lines are just projectile electrons or electron travel. Squiggly line is X-ray creation. So what we had is an inner shell electron ejected, and then our next shell will be our K shell. I'm sorry, our K shell is the inner shell. The next shell will be the L shell. L shell electron drops into place, and you get an X-ray creation. So what the energy level of that is going to be equivalent to the difference in the binding energies of the gravitational pull that the nucleus of the atom has on that electron versus this electron. So if we think back to a solar system, if let's say this was Earth and this was a near Earth orbit, then what's going to happen is we're going to get orbital decay in this. If this was a satellite, then it's going to crash into the Earth a whole lot sooner than what this one is. And that's because the gravitational effects closer to the Earth are greater than they are further away from the Earth. So up here, that's what we're talking about. So we have greater gravitational pull here, lesser gravitational pull here. Our characteristic X-ray photon creation is going to be equivalent to the binding energy, so the gravitational pull, so to speak, on this electron versus that electron. So this minus that gives us the energy level of our characteristic X-ray photon. So that can happen with any one of these electrons, or possibly even a free-floating electron. And so the actual energy level of our characteristic X-ray photon can be a number of different levels. We're only going to recognize one, and that's going to be 69.5. The reason we call it characteristic is because it's dependent on two things. One is how close is the electron to the nucleus of the atom. So that's number one. The closer the electron is to the nucleus of the atom, the greater the binding energy. And two is how big is the nucleus of the atom. The bigger the nucleus of the atom, the greater the binding energy. So what we use in the X-ray target is going to be tungsten. So it's going to be characteristic of the tungsten atom. You change the type of metal that you use in the target, and you're going to completely change that characteristic X-ray creation. So it's characteristic of the tungsten atom, and what we're going to recognize is 69.5. I started this recording, or the first recording, with the question, work all those formulas? And the answer is no. Again, just know how it is that the different components interact and what the different components are. You're not going to have to work any of them. One thing that you might have to recognize, though, is the difference in heat between Celsius and Fahrenheit. And the question is really pretty generic. So boiling point in Fahrenheit is 212 degrees. Boiling point in Celsius is 50. I'm sorry, I just kind of gave that away. Is 100. So um, the numbers mean things, right? So if you have 50 degrees Fahrenheit, then it's pretty cool, and that's what I woke up to this morning was 50 something degrees. It's kind of cool. 50 degrees Celsius is halfway to boiling, so it's pretty significant. So heat, though, is the main thing that we have to deal with in the X-ray tube. So what we mainly get in the X-ray tube is not X-ray creation, it's not even light, is heat. So heat, remember, the definition of heat is kinetic energy at the molecular level. And so what we're going to see then in the X-ray tube is creation of heat. And the different ways that we're going to have to deal with it, and I'll back up to the X-ray tube. The different ways that we're going to have to deal with it is convection, conduction, and thermal radiation. All right, so convection, let's start with conduction. Let's say we create all the thermionic emissions here, and I deposit every one of them here. And let's say I don't rotate that anode. This thing being completely metal, it's eventually going to heat the entire anode. So think about if you're out camping and you're using a cast iron skillet. If you're using a cast iron skillet and you put just the skillet over the fire and you grab the handle on the opposite end, is the handle going to be hot? And it will. You're probably going to want to wear a glove, and that is because it conducts throughout all of that metal. So conduction is spreading through touching. Convection is another thing that you might be somewhat familiar with in convection ovens. So if you have a convection oven and you turn on the convection portion of it, what you get then is the spreading of the heat around the oven because you got a fan that circulates the heat. So all your ovens are going to have hot spots, and that means that if you put your food in one specific place on the oven, it's probably going to cook faster than somewhere else. But if you hit convection, it'll spread all those all the molecules inside your oven around and give you a more even bake, right? So how that applies here is this entire thing is going to be inside of a housing that we'll describe later on. But we've got inside this housing, we've got oil, but also we've got room for a fan. So what happens is that whenever you this whole thing again is surrounded by housing, and there's oil inside of the housing, but there's a fan that can blow air across that oil. And then it becomes kind of like drinking coffee. You drink coffee or hot chocolate or something, and it's too hot for you, you blow across it. The purpose for that is to move some molecules out of the way to cool your coffee down. And it's the same thing that we use convection for in the X-ray tube housing to cool the oil down. And by cooling the oil down, we can cool the X-ray tube down and extend the life of the X-ray tube. And the other one is thermal radiation. So you remember from earlier in the last lecture or the lecture before, radiation just means spreading energy spreading over a distance through space. So we're going to send the electrons across the X-ray tube, and they're going to interact on the anode. The entire anode is going to heat up, but the heat's not necessarily going to stay there. So what's going to happen is it will radiate out to this glass. So this is a glass or possibly a metal envelope. And that's what we'll call the X-ray tube. The the vacuum tube portion of the X-ray tube, the glass that you can see is an envelope, right? Glass envelope. So it's going to spread to that even though it's not touching it, and that's your thermal radiation. So we're going to conduct across the anode, we're going to thermally radiate out to the glass, then we're going to conduct into the oil, and we're going to convect, all for the purpose of extending the X-ray tube life. Ooh, so this brings us up to the end of chapter 2. I hope this was helpful. If you have any questions, again, ask in the comment section so that anybody reading can learn from your question. So I would appreciate a thumbs up for the video. I would appreciate a subscription if you're not already a subscriber. And I'm going to try to get another video out today, and the video today should be preliminary steps in chest radiography. So possibly 2 more this week. The actual chest radiography, PA and AP chest radiography, but the preliminary steps. I kind of tried to ferret that out so I didn't have to cover that in every positioning video that I do. So watch for that. I hope to have that out later today. Thank you very much for watching.